All right, hey guys, we're going to get going again on day 2 or part 2 of this 10.1 section. It's just really what we're going to do is continue with these parametric equations. We're going to actually do some real story problems, okay? This is the fun part of math where we get to apply it to a real life situation. And like I said before, it's going to be a lot of physics. If you've taken physics, this is going to be a review. Okay, so let's just touch base again on what a parameter and a parametric equation are. Um, Big thing to take out of it is the t is not one of the axes, okay? But for equations that have x and y, it's in terms of a parameter t, okay? For pretty much every one of these problems we're going to do, it's going to be time. It's pretty much always time, okay? All right, so that's stuff we did yesterday. We're going to hop on down to these general equations. Okay, so we're going to start breaking down these parts of our equations that we got to remember. And we're going to use these to calculate, throwing a ball, throwing a disc, hitting a baseball, different things like that. Okay, so the first thing, these equations, okay, they're going to look like this. T V initial, I call it V naught sometimes, V0, think about it that. It's the first term, the initial. Okay, cosine theta. Okay, plus the distance initial. All right, and that distance initial is talking about the horizontal distance. Okay, so that would be like if they're saying you're shooting a free throw. Okay, and your toes are on the free throw line, but if you think about shooting a basketball, when you take that shot, you actually release the ball in front of the free throw line, okay? No one shoots straight up, okay? They push the ball forward and they release out in front of them. So in that instance, your distance initial would be something, okay? In most cases, it's going to be just 0. Okay, and that's because, like, if you think about you're kicking a soccer ball, the ball's sitting on the ground. When you make contact and kick it, it's at the starting spot and it leaves the starting spot. Okay, it's not starting in front of the starting spot. Okay, we'll talk more about that. I'll try to make that clear with different examples. All right, so for now, for our y equation, we're gonna have t, our velocity initial. That's what that v is. Sine theta plus 1/2 gt squared, okay, plus h initial. All right, now our h initial is our vertical distance, starting distance, okay, and the good way to think about that is like if you're hitting a baseball, like how high above the ground do you make contact? Okay, that would be your initial height. All right, if you're throwing a football, how high above the ground are you releasing it? All right, football is actually another good one for out in front of you. If you're throwing a football, you release the ball out in front of you, so that would be your starting distance. But with that going forward with those problems, just think about it as if they give you the information, you'll use it. If they don't give it to you, it's going to probably be a 0. Okay? Okay, so now our variables are defined here. Like I said, our initial velocity, our angle of release, initial height, initial time, and gravity. That's the big one, okay? Don't start getting caught up doing all these conversions, all right? If it starts in meters, if they're giving you problems with meters, use this. If they're doing feet, use the feet, okay? The big thing is, notice that it is also negative, okay? It's negative, think about it. Which direction is gravity going, okay? Another little physics thing, if we have our black box, you always see the force of gravity going down. Normal force is the force of if it's sitting on something going up, whatever, if you're adding any horizontal forces to it, okay? If you guys don't know what that is, don't worry about it. It's just something to help people who do, okay? The way our graphs are going to look is we're going to have our vertical distance over time. This is all going to be over a period of time, okay? T equals time. All right, if we got our x, we got our y. This is going to be our vertical distance. This is going to be our horizontal distance, okay? Vertical on the y, horizontal on the x. Okay. One last thing. Oh yeah, our theta, put it in degrees. We're going to do it always in degrees. Okay, shouldn't be doing radians for any reason. It sounds crazy anyway. Okay. Let's slide on down to some examples, okay? Best part of the day right here. All right, number 5. Or, excuse me, yeah, it should be number 5 for you guys. Some of these numbers are different for me. Okay, so we have a rock is tossed at an initial velocity of 50 meters per second at an angle of 8 degrees with the ground, okay? After 0.8 seconds, how far has the rock traveled horizontally and vertically? Okay? So first it's asking us to solve it algebraically. So the first thing we always want to do, let's write up our equations, okay? So we're going to use our general equations. Okay, let's start by writing them over here. So our x equation is going to be our, well actually, before we even do that, let's start listing our data, the data that we're given. So our time is 0.8 seconds. Okay, our initial velocity is 50 meters per second. Okay, our theta is going to be 8 degrees. All right, what we're doing is we're looking for our x, we're looking for our y. Okay, so we're going to have our equations over here. Our x equation is going to look like that 50 out front times t cosine of 8. Okay, our y is going to be our 50t sine of 8 minus, because remember that negative gravity makes this into a minus 4.9 t squared. Okay, and I got that 4.9 because I just already did the 1/2 times 9.8. Okay, 1/2 times 9.8 can get you a nice 4.9. All right, so we have our equations now. We are trying to find out what our x and y is, what's our distance, our height, and our horizontal and vertical distance at a t equals 0.8. Okay, so all we're going to do, plug in 0.8 for t. All right, when we do that, we should have x equals 0.8, 50 cosine of 8. We should have y, that's a 0.8, 50 sine of 8 minus 4.9, 0.8 squared. Okay, another thing, guys, these are calculator problems, okay? Make sure you put the parentheses where you should, so you do the order operations correctly, and make sure, double check before you just hit enter. Okay, so what you should get your x equals 39.6 meters, and your y equals 2.4 meters. Okay, so now if you graph that point, that would tell you where the ball was exactly. All right, so now B, they want you to graph it, or they want you to solve it graphically. Okay, remember, you want it in parametric in degrees. Okay, remember our window. We should have our T min should equal 0, our T max should equal 10. Okay, we're looking at something that's after 0.8 seconds. So if we put 10 in there, that's fine. Okay, then our T step, all right, remember what I said before, our T step, you want to put it in terms of like what your T is being counted in. So in this case, they're looking at 0.8 seconds. So I'm going to make our T step 0.1. Okay. Now, when we do our x scale is going to be from, our x is going to be from 0 to 100. So x min max, I'm just going to put it like this, 0 to 100. Our y is going to be 0 to 8. And our scale for our x is going to be 10. Our scale for our y is going to be 1. Okay? So now here, what you would do is get on your calculator. All right? put those equations in there, just like our original equations without the t plugged in. And then when you get your graph, it should look something like this. Okay. And then all you got to do is, since we made our step 0.1, when we go to trace, find your trace button in there. All right, trace it over to t equals 0.8. All right, because our step is 0.1, you just go over 8 times. You're going to find x equals 3.96, y equals 2.4. All right, test that out and see if you can do it. Sometimes that's a good way of solving problems when your numbers don't work out or you get lost solving equations. Okay, now moving on to the next problem. Okay, number 6 for you guys. All right, we got another story problem, which I love. Okay, we got D Nice shoots an arrow with an initial velocity of 65 meters per second at an angle of 4.5 degrees with the horizontal at a target 70 meters away. Okay. If Denise holds a bow 1.5 meters above the ground, when she shoots the arrow, how far above the ground will the arrow be when it hits its target? Okay, so think about that question. It's asking how far above the ground it'll be when it hits that target. So we're looking for our height, our final height, or our height at a certain point. Okay, so our height at the distance of the target. Okay, so let's identify some of our values they gave us in here. And the other thing is it says 4.5 degrees with the horizontal. All right, that just means they're measuring up from the ground or from wherever your starting height is. So from the horizontal measured up 4.5 degrees. Okay, so let's list our points over here. We got our initial velocity, which is going to be 65 meters per second. Okay, we got our theta, which is going to be 4.5 degrees. We got our x. All right, in this case, our final x, because that's what we're looking at. What is our final horizontal distance? The target is 70 meters away. Okay, they tell us that we're holding the bow. So right here's our initial height, 1.5 meters above the ground. Okay, and what we're trying to solve is our final y when we want to know when it's x equals 70. Okay, right? We're trying to find that height of the arrow when it reaches the distance that target is away. Okay, so let's write up our equations. Start plugging in our values. Sorry, that's a 4.5 plus, this time I wrote the 1/2. Notice I actually have something in there for my h naught, that 1.5. It's not 0. Okay. So now we want to find out what our time is. Okay. So we need to find out what our y is at that distance. So we need to find out another variable. We got to find out what our t is at that distance. Okay. So if we're going to find out what our t is at the distance the target is, 70, we're going to plug that 70 into our x equation. Okay, and we're just going to solve for t, just like we did in the previous section. We're solving for t, plugging it back into the other one. Okay, so if you do this real quick, you should get t equals 70 over 65 cosine 4.5. All right, and you should get your t equals 1.08 seconds. Okay, so we know it only takes 1.08 seconds for this arrow to travel to the to the target. Okay, now we can take our y equation and we can plug in our time that happens at our distance of 70, and it should tell us the height of the arrow at that point. So we're going to take our y, start just plugging stuff in. Okay, the big thing with this stuff, guys, is organizing your data so you can just plug it all in. You know exactly where it goes. Make sure you fit it all on the page. Okay, got it. Okay, again, toss all that in your calculator. Okay, make sure you have your parentheses in the right place. You should get that your final height is 1.29 meters. Okay, that's what they're asking. How far above the ground will the arrow be when it hits its target? So we're assuming it's hitting its target. The target's big enough that it would hit it. Okay, we're assuming that we're shooting the arrow straight. It's not going to fade right or left. All we're really taking into consideration is the height and the distance it's going. Okay, let's move on down to the next one. Okay, last one for the day. Or, excuse me, not the last one. Second to last one for the day. Okay, it says on the 6th hole, Greg Norman selects a 5-iron. He estimates the distance to be about 200 yards to the hole. Okay, Norman's swing provides an initial velocity of 150 feet per second, and he hits the ball at an angle of 25 degrees above the horizontal. Okay, determine where Greg's shot lands. Do you think his shot goes in the hole, assuming that his shot was directed straight at the hole? So again, they're saying it doesn't go left or right. Okay, so let's write out our information to start. Okay, we got that our x is 200 yards, or I'm going to do this conversion now, 600 feet, right? We're just doing that for terms of our gravity. We don't have, it's easier just to convert this than to convert our gravity, okay? So 600 feet, our initial velocity is going to be 150 feet per second. Okay, our theta is going to be 25 degrees. And what we're doing is we're looking at our y. We want to find out where the ball is at when it's at that 600 feet, right? So we're measuring the height when it's at 600 feet. If it's at 0, we know it's dropping right into the hole at that point, okay? If it's 10 or if it's 20, if it's some height that's super positive, we know that it's above the hole and it's going past it, okay? If we get a negative number for at the hole, like it's the ball's below ground, that means that it's landing well before, okay? So let's start out again by writing our equations, okay? Let's just write these right here, okay? So we're going to have our x equals 150t cosine 25 degrees, and then we're going to have our y equals 150t sine 25 degrees minus 1/2, 32 feet, remember, t squared. Okay, remember the ball's starting from the ground, so we don't have any starting vertical height. Okay, we're gonna, again, we know our x distance is 600, so we're gonna plug that in, solve for t. Solving this into, or plugging that into our x equation, solving for t. Okay, we should get t equals, I'll do this step, 600 over 150 cosine 25, which equals 4.41 seconds. Okay, plug that into your y equation. Sorry about that. Okay, plug that into our y equation. 25 minus 16 squared. Okay? So, you could, so when you plug all that into your calculator, what you're going to get is your y equals negative 31.6. And you're going to see that negative number, you're going to think, wow, that's weird, that's crazy, it doesn't make sense. All right, if we have our graph right here, right, we know it's going to do something like that. All right, let's just say that's going to be our 600 feet. Okay, look, right there, we'll just say is our negative 31.6. Okay, so they're just saying that at 600 feet, that ball would be, if there was no ground there, if it could go through the axis, it would be at negative 31.6. All right, we know that's not possible. We know it's going to hit the ground. So what's going to happen, what we can assume is that it'll hit the ground, bounce, and it has a chance at hitting the goal. So to answer this question, you could say it lands before the hole, and it could potentially bounce or roll in. Okay? If it was going past the hole, you would say, oh, it's going past the hole, there's no chance of it going in. We're not going to take into consideration, backspin and all that stuff. I'm no golf expert, but we're not going to think about that. Okay? We're going to do one last equation, or one last problem today, so I'm going to do it on a blank sheet, though. Real quick. Okay, so this problem says the parametric equation for the path of an object launched from the ground at an initial velocity of 72 degrees. Okay, so this is a problem that has a couple parts to it. So the first thing is it wants us to write a parametric equation that's launched from the ground, right? So our initial height is 0. It's launched from the ground. Its initial velocity is going to be 150. Okay, because it's going at a velocity 150 feet per second, and its angle is going to be 72 degrees. Okay, so the first thing they just want us to write an equation. Right, we plug that into our general equation. All right, this is just to help you get some practice, plugging this stuff in, understanding what they're asking for. Okay, part B asks, after 1.3 seconds, okay, how far has the object traveled horizontally and vertically? So they're giving us a t to plug in. Okay, so all we got to do now is, let's just say, we're just going to say at 1.3 seconds. Okay, so we have x equals 150, 1.3 seconds, cosine 72. We have y equals 150, 1.3 sine 72 minus 16, 1.3 squared. Okay. What we get for these are 60.3 feet and 158.4 feet. Okay, so they gave us a time. They wanted us to find where it is horizontally and vertically at that time. Okay, now they're saying, next question, let's scroll up a little bit. When does it hit the ground? Okay, so now they want us to find out when the ball will hit the ground. Okay, so all that means is, when does y equal 0? Okay, so we're going to just start solving for zeros. All right, in this case, when we set y equal to 0, right, when our y equals 0, we get a 0 equals 150 t sine 72 minus 16 t squared. Okay? With this equation, we got t's in both of our parts, so we can just pull that out, right? We can pull out the t. Okay, if there was an extra number there on the end, we'd have to use the quadratic formula. But luckily, they didn't make us. Okay, 1t still left there. All right, that's 150 sine of 72 degrees minus 16t. Okay, I pulled that t out. Now, you can look at it as this, right? We can just kind of use our factoring skills here. We can say, okay, well, we know 1t is 0. Okay, so we have a y equals 0 initially. All that's telling us that t out front, it's telling us that we hit the ball from the ground, all right? The first time, like when the ball is touched, it starts from the ground. So that's the first one. So we know that that extra hunk inside the parentheses will tell us our finishing time, right? So if we solve this for t, we get 150 sine 72 degrees over 16. Okay, you plug that in your calculator, you should get a t equals 8.92 seconds. Okay, so at 8.2 seconds, the ball hits the ground. Okay, that's its final. All right. The next question asks us, how far will it have traveled horizontally when it hits the ground? So we want to know its horizontal distance, or its final horizontal distance, okay? Luckily, we just found out its final time. So all we have to do is take the final time and plug it into what the equation that tells us our horizontal distance, which in this case, which is always going to be our x. Okay. Right? Let's see. I'll just write that up here. Final horizontal distance. Okay. So now, again, this is just a calculator problem. Find out our horizontal distance. All it's going to be, plug it in your calculator. 413.5. Okay, something's going on here. 0.5 feet. Okay, I'll write that again. 413.5 feet. There we go. Second time's a charm. Okay. Final question, what's maximum height? Or not final. Max height. Okay, to find the max height, right, we know that our graph is a parabola. So our max height is going to be the midpoint of our graph, all right? So it's when our time, our final time, is cut in half. Okay, so halfway between the two zeros. It's going to be our time in half, which is going to be 8.92 over 2. Okay, which is going to give us 4.46 seconds. Okay, so now we know what halfway through our time is. We're going to take that in, plug it into our height. Plug it into our height parabola, or I'm sorry, our height function, which is going to give us this y equals 150, 4.46 sine 72 minus 16, 4.46 squared. Okay, when you plug that into your calculator, should get a nice y equals 317.99 feet. Okay? All right. So have some fun doing these homeworks. I actually like this kind of math because it's a real story to it. It's not just numbers, okay? You're thinking, you're doing some critical thinking, you're doing some problem solving. This is close to real life type stuff you'll have to do in some major, some career somewhere. All right? Hit me up with questions. You guys know how to reach me.